Hi, I'm Cliff Click. Maybe some of you have seen this slide, so I'll be quick. I've been around the block a few times, doing, in this case, distributed computation for, my first real distributed systems were like 35 years ago on Z80 mobs. It was quite a long time ago. So this is a talk about a distributed key value store. It is not about H2O. Okay, what is H2O and why did I mention it? Well, it's the platform with the key value store inside of it. So I'm going to mention it because it drives the business logic decisions, which changes the design parameter points for the key value store. So we've made some different key value store decisions than some of the other people that maybe you've been watching, and I'm going to explain why, and then we'll go into what goes on here. So H2O is a platform for doing machine learning on big data, big math. It's a parallel, tightly coupled in-memory computing. So it's parallel distributed nodes, multiple JVMs running on multiple servers, but tightly coupled. It's very fast. So I give an example here, 7 terabyte data set doing a logistic regression in 90 seconds. That's about 10 to 100 times faster than the nearest competition. So in some senses, it's sort of easily the world's fastest machine learning platform a decade after we came out with it. You do end up with a lot of cross-node communication. Sometimes it's because you're moving big data around, but if you move big data around a lot, you spend all your time in the network stack and you lose. So most of the time, the big data stays put, but you still do a whole lot of command and control. There's a lot of reasons to send intermediate temporary results, decisions on which way the algorithm is going to go. There's a lot of reasons to do coherency across the cluster, and that turned out to be best done with a key value store. So we're coding for big math. I'm going to give one quickie slide here. The data is treated as a large 2D array where large can be trillions of rows. So it works great for thousands of columns. It works sort of pretty damn good for tens of thousands of columns. At about 100,000 columns, the loops are parallelized the wrong way. Okay, fine. But for row count, there's no limit. And we do this fairly automatically. That is, we do automated scale out, not truly automated, but it's darn close. We ask you to write in a coding style that turns out to be very natural for serial sequential coding for mathematicians. It's like Fortran-y C code written in Java. Most simple Java just works and scales out naturally. And the cluster behaves like a large shared memory machine, where large can be terabytes of RAM. There's lots of code gets written, most of it by mathematicians who are not actually distributed systems engineers. There are a lot of edge cases you have to take care of. There's some special algorithms that are not typically written by mathematicians, such as distributed sort. So it became difficult in the early eras of H2O to have people try to code to distributed style, and we kept wrestling with how to make that work. And we ended up with one style for the big data, which we're not going to talk about, and another style for doing all the command and control, which turned into a key value store with Java memory model consistency semantics. Why Java memory model on a distributed system? Because we could find lots of people who understand that model. It was a well-defined, well-discussed model. People get it. It does require you to have some exact consistency semantics, but you also needed to have bulk speed. We had to have the way to efficiently move big data around when it happened. Okay. So, performance is a concern here all the way down the line. Most of the time, H2O will do, in-memory computation. That's 50 gigs a second to your memory. That means a single node can do a terabyte in like 20 to 30 seconds. A big cluster can do a terabyte in under a second. So the data is mostly local most of the time, and when you have to go over the network, you load it straight from NIO buffers into CPU registers, and it never hits anything else. We do a lot of custom serialization. I'm not going to go into that today. A very aggressive compression. It was as fast as Cryo when I last tested it some years ago, without any setup costs. You just wrote Java code without any kind of setup, and we would give you, basically network bandwidth limitation speeds for doing communication here, for serialization. So it's the Java memory model done distributed. And what is the memory model? What are the parts that are interesting? There's a volatile notion, which has strong ordering requirements. And there's non-volatiles, also well-defined, and mostly anything goes. You're not allowed to invent things, but the orderings are clearly sort of whoever, somebody wins, but you don't know who. So we can find lots of engineers who understand that model. It becomes much more difficult to actually design and build a distributed system that does this. In my case, I had long talks with a guy who is an expert hardware cache designer. He did the cache coherency protocols both on the Sun big multi-CPU servers and the Azul system server. Okay, and then I'm going to do this disclaimer taken from lesson from Heidi here. I don't know if she's in the audience. This is distributed systems talk. So you think about the CAP theorem. I gave up the CAP theorem in a funny place. I gave up on the P instead of the C or the A. What does that mean? If a node dies, the cluster dies. This is not about reliable distributed systems. There was an effort in the beginning to have a really nice, reliable key value store with replication and nodes could come and go and all that kind of stuff. And that market was saturated, and we pivoted over to machine learning, and having a robust, reliable system wasn't necessary. Because it's too fast to reboot the system, I don't care that it's up all the time. And because I'm not trying to be a persistent store, I don't care if I lose things on a reboot. So I don't want to replicate it because it's too big. I can't hold it in RAM if I have to replicate, right? That's the definition of big. It's much, much bigger than my RAM, and I'm in memory, so I only have one copy of the data. And then rebooting a cluster means, it's actually a couple seconds to reboot. If you lost a 100-node cluster on Amazon, you lost a node, you reboot, it's a 99-node cluster, and you have to reload the data. Well, every disk spindle runs at its max throughput. The actual mask as given by the vendors is some ridiculous number, but as achieved by most modern OSs, you can get 100 megabytes a second. So it's fast enough, and you reload the data fast enough that we didn't bother with any sort of reliability. If you lose a node, you lose the cluster. Now, I am going to be reliable, do something about reliability of the network communications. So I'll get to there in a little while, but UDP packets that are dropped or reordered are totally handled. But if a node goes away and never comes back, the cluster's dead. Okay. So Java memory model, but distributed. So I end up with 2 layers of memory models now. I have within a JVM and across JVMs. So within a JVM, it's the normal Java memory model given to you by the JVM, right? It's single loads and stores, have a key, which is really the address of your pointer, and you have the usual semantics we're all used to. The distributed version, the loads and stores to individual Java objects turn into gets and puts. And the address becomes this cluster-wide address space. And there's some efficiency operators thrown in that says bulk move this array to that space in some way that gives me sort of the max throughput I'm going to get. And you get a classic distributed key value store, but I'm going to have exact consistency semantics. So that's a little different. I'm going to be exact and I'm going to be fast. So distributed key value store, put with a key and a value in one node, some other node, I can do a get and get it back, right? But I'm going to be exact. So if I have conflicting writes, eventually one will win, but also there's never a time when people will get different versions from the key value store. And the keys are used for all kinds of things. Internally, they hold the big data, that's the data sets, machine learning models, results. Externally, it's all this stuff. Internally, there's also a bunch of temporaries used during the model building process. Score data, there's all kinds of cached results floating around here. So the system gets a heavy use. And in fact, in practice, you could see millions of cross-node key communications a second as sort of a standard everyday thing. Within a node, it's even faster because everything will cache. So this is a hardware-style cache coherency protocol. You notice funny spelling of Mosey here. It's not the Mezi I was doing earlier. All values can cache locally, and that's sort of a crucial thing for speed. And if it's cached locally, it's nothing more than a hash table lookup to go get a value. So if I have a key in my hand, the first thing I always do is I check the local cache. And if I hit it in the cache, I win. That is a cache coherent perfectly correct value. If I have puts, they can be local, they can be remote. If I have puts to different keys, they all can go run in parallel, and I still remain my consistency. The reasoning being that I want to hit the network bandwidth, not the network latency for any bulk operation. So in particular, if I'm producing a huge temporary value and it's much bigger than my local RAM and I have to spray the value around the cluster, I can just spray it around the cluster in whatever order I can most efficiently push the data out and have it still be exact consistency semantics. One of the other things going on here is the keys are pseudo-randomly placed around the cluster. In hardware, people do hashing all the time. And the goal of that is to make it difficult for you to have a hot cache line, right? When everyone wants to hit the same thing. I'm doing the same thing for the same reason. I don't have a hot node. So what do I mean by that? Keys all have a home node. The home node serves a bunch of purposes. It's the ultimate truth for all your gets. It's where you decide upon racing puts who wins, who loses, and what order the puts are applying to. It atomically executes transactions. It has the coherency semantics are baked into the home node. But you don't want the home node to be a hot target for everybody. The same node to be hot for every key, right? So the home nodes are pseudo-randomly placed, except for big data, which we do a forced round robin, so we get a uniform distribution with mini batching. I won't go into much detail there. It's you do mini batching because you get a lot of edge cases. You do stencil calculations, you get edge cases where you walk off a chunk of data. Most of the time, that edge case walks onto a piece of data that's still local, and so the cross-node communications for chunks of data always remains, most of the time remains local. So it's an efficiency hack for doing stencil calculations. Okay, I mentioned keys, so values. Values contain your payload that you think about, plus also they track coherency. They track what nodes have a replica, because you have a lot of replication. That's caching locally requires replication. If you write to something that's replicated, you have to go find all the replicas and kill them. That's tracked by the values. They're used to force orderings of different writes. That's the decision point is made with the value object. And it turns out you need a count of outstanding in-flight gets. This would be, in the hardware model, it would be loads that left my core and ran off to main memory and didn't come back yet. They're still in flight. So I have gets have the same concept. They leave the home JVM, they cross the network to some other, and there's some result coming back, and it hasn't completed yet. I have to count them to make sure I keep my exact consistency, and I have a set of caching nodes, and we'll go to an example here pretty quick. Yeah. So I'm going to use a 4-node cluster. I'm going to do some little machine learning kind of work here. I'm going to pretend I started with a new model stored on some node A. Other nodes want to go compute error metrics on the model, so they're going to grab a copy of the model and apply it to their slice of the data. Every node has 1/4 of the slice of the total data. Once they're done doing that, they do something else. Somebody decides he has a new model. He's going to promote it. So he's going to go publish a new model. Everyone's caching the old model. They have to go be told there's a new model and made sure that there's an exact consistency. If they go fetch, they'll get the right version of the model at the right time. Okay, so let's look at some examples here. The example. There's a single key in this example because I don't need multiple keys to make this go. But if I do multiple keys, it's almost exactly the same until you do multiple stores. We'll get to there if we get there. There's an initial value, the model. It's going to start on some node A, and nothing's in flight. So I'm going to break down this little funny box. We're going to see a bunch more of this. There's a node A. That's a JVM. Within that JVM, there's a key and a value. The key I'm not going to write in my node because I'm going out of space in my slides, but there's a value, and it's v1. It's version 1 of this model. I only say version 1 to distinguish it from version 2. I don't actually have a version number in the value objects directly because I don't need it to make it work right. The garbage collector saved me from ABA. And there's no gets in flight. That's the 0, so the system's quiescent. And there's only one replica. It's on node A, the home node. Okay, so that's the starting. That's the initial conditions. It's actually a 4-node cluster. Other nodes are not cached anything yet. Somebody wants to get a copy of the model. So let's start with B here. B says, I've been told to go run the error metrics on this model. I have the key, the name of the model. I don't have the model. So go get the model. Well, I look in my local cache. I miss. I have to go to home A. So I'm going to go to A. How do I get there? I hash. I hash the key. It tells me it's node A. Now, at minimum, I have 2 packets, a round trip here. I have to send the key to A, and I have to fetch the data back. In my case, optimization, if it's small, you went with a UDP packet with obvious timeout and retries, and that's a reliable UDP. And if it's big, I want congestion control, and I do a TCP thing. The model's probably bigger than a fat UDP packet, so there's probably a TCP opened up for that channel, but it varies. A lot of the communication, a lot of the command and control packets are very small, and we do send them with UDP because it has lower latency than TCP by like 3x. And that turns directly into how fast I can start and stop big data passes. Okay, and so I get this chart for just a cache miss from B to A. And I'm going to break it down and walk it through here. What's going on? So there's a get. B says, hey, I want this key. I miss. I have to go do something about it. So I know where it lives. That's home node A because I looked at the key and hashed it to A. And I fire off request to A. That's a UDP packet. Hey, Mr. A, tell me this thing. A gets that packet at some point and just says, okay, I need to send a copy of this thing off. I'm going to raise my outstanding get. There's a pending read off of this value. And I'm going to say it's B asked for it, so I'm going to say B is going to have a cache, and I send it back to B with the result. Right? So B starts receiving the result, and again, the results go big or small according to UDP or TCP, according to the size of the thing. Once B gets a copy, 2 things happen. He's going to record it locally in his cache, and he's going to begin executing on it. So he doesn't have to wait anymore for round trips to A. He's got a copy of the data. It's valid at that time. He can take it and run. But he also tells A that I got it, because otherwise A doesn't know that it actually happened. If you use TCP, that happened under the hood in the TCP protocol with UDP packets been sent back and forth. I'm manually doing it because I can get there faster than using TCP, but I have to do what TCP would do, which is send a packet to A saying, okay, I got it. And A can lower his get count down to 0 because we're done with the, I wonder if this thing works here. No. This. Oh, look at that. Yeah, there's a 0 there. I don't know if you can see that. And then that went from a 1 up here to a 0 there. And that just says no one has an object in flight headed out. And we'll see that when I start doing puts in order to get my ordering correct. What happens if I do this with multiple nodes? Right? So a bunch of people say, hey, we need a copy of this thing, so we're going to do overlapping. And what happens? Okay, the chart got bigger, but it's not going to be horribly more complicated. Somebody sends a packet to A. Oh, he got another packet. And he begins processing them. And as he processes them, this is actually done on multiple threads in A. So this is distributed, but within a node, it's parallel. And so the get counts and the ABCDs or bit set are all concurrent structures, and they're modified concurrently by different threads that are responding to the packets that are coming along. And at some point, A can start sending packets back. There he goes. He sends a packet to C. C picks it up and begins recording it. Once C installs it, C can take off and go. He's not waiting for A or D, or he doesn't know anything about D at all. He just takes off and runs with the value he's got. And C eventually acts back. D's recording here. D acts back. And eventually my count drops down to 0. And I have knowledge that everyone in the cluster has a cached copy of this key. And now that it's fully cached, everyone who does a get can just do a hash table get locally and hit in about 150 nanos to do a hash table lookup. Okay, what if I need to do a new model? So somewhere along the way, somebody decides I have a better version of things and I want to write. So this is just like you wrote to a volatile object in a Java heap. There's some sort of ordering operation going on here. Once I do the write, I want to be able to know that I can get it myself fast. So this is same as Java memory model. I can do a get after a put. against my own object, and I'm guaranteed to see what I just wrote sort of immediately. But I have to write it to the home node, or the rest of the cluster won't hear about this new object. So I have to do a write to A. Now, if I'm non-volatile, I can just carry on. I'm done after I tell A about it, and other nodes will hear about it when they hear about it at some later date, and I don't care that they know or don't know that I wrote in whatever order. If I'm going to be volatile, then there's an ordering constraint, and I have to wait till A comes back and tells me, everyone knows about your write. Right? So one is go without waiting, one is waiting, and you get to pick, same as you do in Java, by choosing to either lock it or volatile, but there's no locking in a cluster, so it's volatile instead. So node C is going to do a put. He's going to cache it locally, he's going to write to A is going to do some update from version 1 to version 2, he's going to lock it against other gets and start sending out invalidates, and we're going to run through the eye chart again. Right? So here's the eye chart. C writes the new model. Hey, I got something new. He does a put into his local cache. He updates it. He marks it as pending. So here is a write I have written. It has not come back yet as being accepted by the system as being the new value. So I'm in an inconsistent state. And because I don't have any racing rights, it doesn't matter that it's inconsistent. But if I wanted to be, if I had multiple racing rights, this is the point where it's inconsistent, except if I don't do a volatile thing, I don't care about inconsistency. So then I send it to A, and again, fast or slow, UDP, TCP, depends on the size. Once A gets it, he installs it locally. He updates the hash table he has locally with a new version. He knows that he has a copy. Here, get this thing again. That's the A and C are being cached. And the 0 count says there's no outstanding gets. But the old object still lives on. Let's see here. With a B and a D having caches. And the -1 says no more gets are allowed to happen on version 1. So there is a narrow data race within a single node that says people are installing with puts and people are requesting gets. And at some point you have to atomically draw the line and say, this is the last time I sent out the old thing. From now on, everyone gets the new thing. But I'm not consistent until the last person who got the old thing came back and said they got it. Then I can tell them, okay, you're stale now. Go get, try again. So I have to keep both values around for a while, and I have to know that I have not yet invalidated B and D, and I'm not showing a get in flight. But if I had a get in flight here, I'd have to wait for it to settle before I could carry on. So let's go ahead and carry on. Okay, there's the lock, preventing V1 from being promoted to anyone else. And now I start sending out invalidates to B and D, and that's just a UDP packet that says, hey, you're stale, get rid of your copy. They hand out in whatever order. When people get them, they just drop the thing from their own local cache. Then they send an ACK back saying, I've done it. Until that ACK comes back, the put has not become consistent. So I have to wait to get all my ACKs back. And at that point, node A knows that no one else in the cluster has a copy of the old value for the model. Now C has a new copy, and A has a new copy, but B and D don't have a copy of the old value. And so at that point, A can ACK back to C saying, your put has completed. And then C, now that his put is completed, is allowed to start a new put if he wants to say, I've got a new version of the model, even newer, or do whatever he needs to do. If he was looking for the volatile semantics, he was waiting for the put to come back. It's come back now. Once that put came back, the other ACKs are there to complete the reliable UDP scenario. In case anyone dropped a packet, I can replay after a timeout, but otherwise I don't care. So those don't block any further computation from anybody. Okay, key takeaways. All keys can cache locally, and that is crucial for performance because people who write this code don't want to think about caching or not caching themselves. Some piece of code needs a copy of the model, they say get. Some other piece of code needs a copy of the model, they say get. And you get gets and gets and gets and gets to the same key over and over and over again. Hitting repeatedly in the cache is crucial for performance. So that's cool. The next thing is that once it's in your cache, it's there, it's valid, it's correct and forever until it's invalidated by a put from somebody in the cluster. Okay, the next thing is bulk reads of the same key happen. That's just a publish operation. And you want them to be bulk efficiency again, so they can happen in any order, they don't block each other. The limit is network bandwidth, not latency, to send all the copies of the data around. Once you have a copy of that data, you don't have to wait for any further acknowledgement. You've got a copy, you can begin computing immediately. You do need to send an ACK back, but that can happen in parallel with you doing the math. So there's a lot of latency reduction things I'm doing in here within a node and across the network. I want to make sure I'm doing best effort to get the data around. Puts don't stall a writer unless they're going to be volatile. So non-volatile puts, which totally happen, especially for like big data temporaries where I'm going to bulk puke out a ton of data, no one stalls. In particular, the writer doesn't stall. He can go write, and he can write another one, and write another one, and write another one, and another one, as fast as he can dump them out to the network. But that's consistent locally. If I do a get against a put I just did, I'll get it directly. Bulk puts to unrelated keys also go in parallel, and that's the big data. I'm just transferring it from here to there as fast as I can. Repeated writes to the same key have to be ordered within one node because I don't understand, the home node will understand if the network has reordered packets. So within one node, doing multiple writes to the same key, I do have to have ordering. I do have to wait for the round trip. So that's one of the places you do. However, if I have repeated writes to the same key from different nodes, that's like racing rights in any other programming language or Java. Somebody wins, but there is a winner. The home node decides which one is the winner, and eventually everyone in the cluster will discover that is the winning value. There may be some inconsistency for a while we're waiting to see for it to settle out, but it's not incorrect because you're doing racing rights. All missed gets have to round trip to home because you don't have the data locally. But it's cached forever thereafter, even if it's volatile. Doesn't change the semantics to have it cached locally for volatile reads. Volatile puts, though, have to wait for the round trip to home, and they might have to wait for any outstanding gets to settle first. So sort of the worst case scenario is I'm trying to put from here to there, and I send you the key and the value, and the home node takes the key, looks, and says, I have an outstanding get of the old value. So I have to let the outstanding get complete. I get the response. That guy knows that I know that he has the value. Now I'm going to invalidate him right immediately, and I have to wait till the invalidate comes back, and then I can claim no one else has a copy and promote it out and send it back to the original guy saying, okay, I'm done. So the price is really only paid here if you're rapidly reading and writing the same key. Bulk writes to the same key, bulk writes to independent keys, bulk reads from independent keys, bulk reads from the same key, all work well. It's reading and writing back and forth in the same key. Turns out there's only a handful of times when we have to do that, and that does pay the full cost in order to get the memory model consistency. So the cost model, repeated reads, same key, cache. Bulk reads, limit of network bandwidth. Bulk writes, limit of network bandwidth. Racing readers and writers, it's even better. It's network bandwidth plus you cache locally until you get stomped by the writer told you. Volatile reader, same as a normal reader. Volatile writer pays the cost, right? Round trip plus the cluster and validate cost. Once you get your data, though, you can go compute on it immediately. It's all correct. Even if you have some further background communication to close it out, you have a copy of the data, you're good to go. We also support single key atomic transactions. We ship the code to the home node. We don't ship the data anywhere. The data is too big. So you ship code instead of data. The home node executes the transaction, attempts the atomic update. If that fails, he'll locally retry until it works. You get the same sort of ordering semantics as a volatile get divided by a volatile put. A couple times we do atomic updates for a couple different things. Usually transactions are tiny. And it is single key only atomic transactions. And that's it. This is 30 minutes, right? So H2O is a fun system. I mean, I wrote it some years ago. I haven't messed with it in quite a while. I'm out of the company. But it's a cool clustered big data computing platform. It's a whole different set of talks to talk about what you do with it and how it works. But the key value store is like top notch, extremely fast and exact. Good consistency model, good usable key value store model all around. And that's it.
So, does anybody have questions? No questions, really?
I got one. Yep.
Thank you for the talk. I am curious about atomic transactions. Is there any DSL supported? Because obviously it's not safe to execute arbitrary code on the
Is there any what?
a DSL for writing code for
I'm missing what you're saying there. Is there any?
DSL.
No. So this was all done as pure Java. There's no, and runs on the stock JVM. So there's no special support for anything in there. If you write, system.exit as one of your transactions, well, that node just died, right? So there's no saving you from shooting yourself in the foot. You can take a lock, it's node local only, not cluster wide. So if you take a lock, you're generally wrong. If you do, print statements, it'll only print on one node, right? So it's not a complete distributed language. You have to understand the limitations. That being said, if what your goal is to do sort of bulk math, and the math can get quite complicated, that just works well. The atomic transactions are generally done for control things, like counting progress. Like I'm going to count iterations of the modeling process, and the user has given me so many round trips before I need to stop, trying to asymptotically improve the model. And different nodes are bumping the counter for whatever reason. And when somebody hits 100, they set a flag saying, we're done now. And that's a volatile write somewhere, and there's an atomic update of a counter or whatever. So there's a progress bar show up in atomic counters in these kind of transactions fairly often. But if you write something, like I said, that either locks or kills a node or does I/O, it's generally not sensible in a cluster-wide setting. So yeah, you can shoot yourself in the foot, right? You have to have some discipline in code writing. Does that answer your question?
Okay, makes sense. Well, another question about switching between TCP and UDP.
Yeah.
How can I know whether the data is large enough to switch?
Why do you care? Really, the goal of the system is make it as easy as possible for you to write algorithms. One of the things that has to happen is data has to move around, but the coding style that you see is I have plain old Java objects, but sometimes they're on this node and sometimes they're on that node. But I don't actually see it in the code I write. Magically under the hood, it went from here to there, and that was the key value store going to town. And so the size of your Java object after serialization dictated how it was sent. But that's all about throughput and latency handled by H2O as a systems platform, not exposed to the end programmer. So there's a way to tell, I can tell you what it is, but it's not part of your coding style. You don't have to think about that when you're writing code. So the size is the standard UDP, MTU size is about 1,500 bytes after serialization. Having said that, is your object more or less than 1,500 bytes? Maybe you know, and maybe you don't.
But you did some job to know in advance how to switch between.
I did some job not in advance to switch. So somebody came along and said, put this Java object as a key. I needed to write it somewhere. So H2O then said, I need to serialize it. Oh, there's a bunch of caching done. Maybe I've serialized it already, maybe not, whatever. So somebody serializes it. The serializer produces an array of bytes, generally in a network byte buffer packet directly. If it fit within 1,500 bytes, I hit a UDP packet on it and send it out. If it didn't fit at 1500 bytes, I stopped and opened a TCP channel and jammed the bytes in there.
Okay, it works for put requests, but what about get requests?
It works the same way. The key is always small. Key requests for gets always go UDP. But the sender of the value says, let me look at this value object, let me serialize it. Did it serialize small or large? If it serialized small, it went out with a UDP packet. If it serialized large, I stopped and sent it TCP. It's actually symmetric here, right? It's whenever a value is moved, there is a decision made, UDP or TCP.
Okay, I got it. Thank you.
Yeah. There was another question somebody had over here.
Yeah.
Thank you for your lecture. I have two questions. First question, do you have a distributed GMM? And did you implement, for example, distributed synchronizer, distributed other primitives from Java util concurrent package other than that?
Yeah, okay. So this is a distributed JMM. You have to use get and put instead of just reading and writing in and out of Java objects. So I didn't add a DSL that under the hood rewrote, Pedro's last talk, he basically switched to C++ because smart pointers gave him a function call on reads and writes. Didn't do that in Java. You could imagine doing it. Okay, fine. So were there other concurrency semantics or primitives done? There were a bunch because we were trying to write a sort of convenient to use systems platform, and different behaviors showed up time and time again, and so you had to go around and do it. So I actually have concurrency model that's very similar to the structured concurrency model that was brought about by Roman yesterday in the Kotlin. No concept of Kotlin doing this or that. It's completely independent, but basically I do structured concurrency under the hood. It's not quite the same thing, but it's pretty dang close. In particular, there is a divide and conquer for the big data that looks just exactly like fork join done distributed in bulk scale with a lot of efficiency hacks thrown in the end, but you code it like you're looking at fork join. Okay. That's not the only consistency semantics we have, but that's the common one because a pass over the big data is a MapReduce style thing. And so most of the time you somewhere say big array dot map some function, and it went parallel everywhere, but there was a log tree spread out and a log tree gather at the end, MapReduce, that required a lot of consistency semantics floating around that turned into, that's the common consistency semantics.
Thank you. And my second question is related to big data area. The most popular case from my point of view is usage H2O with Spark in Spark and Water. But I think how both model, I mean Spark has his own internal representation memory, working with CPU caches and etc. with distributed GMM, how it communicates, or it touches only in one point in creating of, I don't know, data sets of vectors for training, etc. Maybe you like this.
So you can find videos of me talking about H2O's internal architecture and how it differs from Spark. They're definitely different. I made a bunch of decisions that led to systems much faster than Spark's, which is why there's some interest to go between the two. And Spark became popular and H2O remains very fast. So there's an interesting thing there. But I got some time. I can talk a little bit about that now, but that's not necessarily what everyone wants to hear. Big data, you do column compressed stores, you store data only in byte arrays using basically value objects done with unsafe. And you compress the hell out of it because the compressed data runs through your memory footprint, your memory caches, and your memory bandwidth faster than uncompressed data. Never, ever, ever do a capital D double, capital I integer because that loses you by like 4x or something. It's horrible. As a consequence, I can do Fortran style math typically faster than Fortran. Yeah, some limited cases. Let me take that back. Some limited cases. Because the data is compressed and because the limitations memory bandwidth, and I'm using 1/8 the memory bandwidth, right? So I actually get 8 times the speed up if the data compresses that well. Okay, that being said, you know, the coding style is different. You write a for loop, which you don't typically do in Spark. You talk about array elements, which again in Spark you don't typically do. You can. And you otherwise write sort of plain old Java code instead of plain old Scala code. So it's definitely a little different. But the target audience is somewhat the same, but the design engineering points were substantially different. I do distributed vectors. Spark mostly does distributed partitions, which are sort of 2-dimensional breakdown. I'm doing sort of a 1-dimensional breakdown this way. What else? I mean, there's a bunch of other stuff that maybe that's a Spark versus H2O, and what does the H2O design point look like compared to Spark? So that's not necessarily key value store things. Why don't we take the rest of this offline and see if anyone else wants to talk about or ask questions here?
Thank you for your talk. I am just wondering, how does debugging, profiling, and optimizing looks
Yeah, exactly.
with distributed applications? Just imagine that your code travels between nodes, and you see that one link between 2 nodes is saturated, and just only gets and puts traveling everywhere. And
right. Okay. So you know, H2O has been around a while. It was definitely, performance was an issue. So how do you design for a system that you can debug and do performance analysis and the like? Okay, so there's a couple of different pieces to that puzzle. First is it runs well as a single node. So you could just bring it up in IntelliJ and run it on your box, and then it's a parallel machine. That doesn't tell you about network latencies. So if you don't have a network latency bug, all your normal profiling tools work on one node with a smaller amount of data, and you debug there. The next thing is that if you have a bug that throws an exception in a distributed system, typically every node throws that exception. And furthermore, every parallel thread on every node throws that exception. So you don't get a copy of an exception, you get thousands of copies of that exception. So as part of the process, when we do that map reduce thing, part of the fun coherency semantic protocol is as people begin throwing exceptions, we limit it to like there's a winning exception, and those roll up in a log tree, and so you get a count. Hey, some thousands of exceptions were thrown, and here is a stack trace. And the stack trace includes the path all the way from the originating node, which might be far removed from where you're sort of conceptually thinking that I launched it at. So somewhere here I said, do a map across this distributed big data. And it went out to this node, to this node, to this node. Somebody did a bunch of stuff, blew an exception. Blew. Everyone, boom, 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 all over the place. Okay, they all come flying back, and then we do this gather thing. We gather pairs and pairs and pairs, and you do the log tree roll-up, and eventually it comes back to where you said map, and here's the stack trace from the original node, plus all the intermediate stack traces, everyone in between, and IntelliJ does a good job of collapsing the replicas, and you get a reasonable stack trace. And that was a lot of work, but it was necessary to help debugging, because you did have a set of bugs that only showed distributed rather than remotely. Like if you did a custom serializer, like if you took the H2O's built-in serializer, you wouldn't die here. But if you wrote a custom serializer because you had some sort of efficiency hack and you screwed up, it would only show if you serialized, which would only happen if you ran distributed, so it only blew over there. Okay. The other one is that you had a bug in your reduction pass, which only happened when your data got big, so you kept testing it reasonably, your algorithm on some amount of data was okay, but when you did a cross-node reduction, there's a slightly different semantics to it than a local node reduction, and sometimes it would blow only distributed, and so again, you would get a remote exception, you had to go gather. Okay, fine. So we did a bunch of stuff with exception throwing and catching. And then for profiling, we put in a distributed profiler, really, not a heavyweight thing. It was a scatter-gather on the log tree where you took the latency of each local map. So the data is broken up into chunks, Every node has 1,000 chunks. You got 100 nodes, 1,000 chunks. You got 1,000,000 chunks, whatever. You got a huge count of chunks. You did a map over a chunk of data. That took some time. You had a bunch of these. They're running in parallel, but you can tell by the relative amounts what's the total lag across them. So you did a log tree roll-up of the distributed costs. Then as you went over the network wire, you took the latency for that too, and we gave you the worst case long tail time between when you launched map and when you got a result back, broken down by, I took a network hop, a network hop, a network hop, the worst case map here, and a network and back, plus the reductions, whatever. So you got that timeline of the losing path. And plus some averages and stats on the typical path. So when the long tail approached the typical, you were done. You weren't going to get any more out of that thing. But there were some profiling tools put in for exactly that reason. Now, the DKV itself, the original implementation would get into various kinds of scenarios where things got very slow or backed up, or you had cyclic, we had to do, what lock ranking is? We had to do lock ranking across a cluster. Stuff like that had to happen. Over time, those all got hammered out. And at this point, the DKV is sort of never the bottleneck. I mentioned earlier, people do millions a second across the cluster. They do, and it's never the problem anymore. If you're shipping big data around, you can be network bandwidth bound, and some of the algorithms get big data as part of their temps, and that's their limitation. But it's not the DKV itself, it's the fact that you're actually shipping a shit ton of data around.
Thank you.
Yeah.
Thank you for the talk. My question is, are locally cached keys or evicted from the store for reason any other than remote update? For example, when memory is low, or they should be evicted, otherwise there wouldn't be enough memory to cache.
Yeah, exactly that. I don't have a good example here. If you're not the home node, you're allowed to evict at any time. And then if somebody asks for it again, you'll bring it back. And the local cache has home data, which is some fraction of the big data divided by the size of the cluster, plus whatever temps the one node is using, and they're all counted with an LRU counter. And when you're low on memory, you get a GC Java Beans callback, says I'm low on memory. You walk the local cache and find the LRU that's not home, and you start throwing things out.
Was the eviction strategy least recently used, or?
Yeah. I mean, you could be smarter, but it didn't matter too much. Here's why. Typically, if you had a low memory situation, it's because you were making data that you were semantically supposed to keep. As soon as you exceeded the size of your memory, the only fallback you have is go to disk, and then you're 1,000,000 times slower, and it's not worth it. So while in theory, we could spill to disk, we had all the right pieces, parts in there, and it actually was tested, and it worked kind of okay, it wasn't worth it. So if you hit that mode, you're better off killing the cluster and restarting it with either a bigger cluster or less data. Okay, or you had to change your algorithm because your algorithm was screwed up, that it was producing too much data you had to keep. If you had to spill, you ran out of memory and you could evict it and then reload it, almost always that was a case of it didn't happen very much, so it was okay. Or it happened in huge amounts. It was a very bimodal distribution, right? It was either I rarely had to evict because I was rarely low on memory, because big data is half my memory and my temps take the other half, but all the little control packets and models and shit, that's like tiny, tiny, tiny compared to the data. So you never had an issue there. You had to have this exact consistency semantics, but actually volume-wise, it wasn't very big. Or you blew it out hugely and you're just like completely dead, and now it was time to restart the cluster with a different configuration.
Thank you.